All right, guys, just give me a sec while I get some things straightened out, and then we can start. All right, so this is now rolling. All right. So, welcome to this last goodbye farewell session, as well as one of the most important sessions of all of this duration that we've been together, which is our O level slash IGCSE P2 revision session. So, again, if you have been looking at the YouTube videos that have been going out uh, really recently, so it's going to be kind of the same format that we are going to talk about some of the common mistakes that you have to avoid. What are some good questions that we can do just to have a quick last minute practice, and also a sort of a paper prediction by my side, which is going to talk about what topics could possibly show up on the paper tomorrow. So you guys might know O level and IGCSE, both papers are tomorrow. So how I've broken this down is into chunks based on the units. So first one is all of mechanics, then you have heat, then waves, electricity, magnetism, nuclear physics, and then lastly, space physics. All right, so let's do a quick sort of run through of things that you are supposed to know. One of these is kinematics graphs. Obviously, we have talked about this in a lot of detail in the theory videos as well as in the past paper practice. So whenever you do get a kinematics graph, always remember the steps that you take to analyze this. And I'm talking about reading the graph even before the question starts. The first one is to determine the type of the graph. The next step is to talk about its features. And then in the third step is when you actually go on to solving the questions that the examiner has set out for you. So for example, if I run across a speed time graph, this is my first thing, which is to identify that this is a speed time graph. The next step for the features is to say that the gradient of this graph would be the acceleration, and the area under the graph would be distance. And now, having established this, is when I set out to actually solve the questions that the examiner would be putting forward in front of me. Right. So this is how you deal with kinematics graphs. You must obviously know all of the shapes and what they mean. For example, this sort of a shape is a increasing gradient shape, right? This sort of a shape is a decreasing gradient shape. So you must obviously have a really good grip on the graph shapes, because the uniform ones are still easy to analyze. The non-uniform ones are basically what are more difficult. Then for the choices of instruments for mass and weight. So according to our new syllabus, mass is measured using a beam or an electronic balance, whereas weight is measured using what is now called in the new syllabus a force meter, or what was previously in older editions of the syllabus, what was called a spring balance, right? So for each of these, you want to understand how these work, because another thing which has not been asked really all that recently, but remember that we have covered this in class in a lot of detail, is talking about which readings change. For example, if we take all of these apparatus to the moon, right? So if small g changes, which readings change? So the answer to this one is that the beam balance reading is the only one which does not change. The electronic balance reading changes, the force meter reading changes. And in a sentence, the answer to this question as to why this is so is because the beam balance works on the basis of comparison. So it compares masses. You can also think about it this way, that, for example, if you had 2 kg and 2 kg masses on the other ends of a beam balance, right? A beam balance, if you also look at your syllabus, it measures masses by comparing weights. So if they are balanced, is because their weights are equal, right? So if they are 2 kg and 2 kgs, so 2 times 9.8, which would be 19.6 newtons are their weights. If I take both of these to the moon, so on the moon, again, their weights would be individually reduced, but are they still equal to one another? And the answer is yes. So this would be balanced. An electronic balance is based on sensors, so this won't give the same reading. And the force meter basically works on the extension of a spring. If the force is less, so the extension would also be less, giving us a reading which would not be the same. Right? So cross means this does not change. This changes, this changes. Newton's third law, again, something which is very frequently confused. Newton's third law, please do not write, if this is asked in your exam tomorrow, please do not write that every action has an equal and an opposite reaction force. You will lose marks if you write this. Rather, you have to talk about it in this way, that if there is an object A and there's an object B, if A applies a force on B like this. So I'm writing this as AB, which is A on B. So B applies an equal and opposite force of B on A, right? So there are really three boxes that you must tick when talking about Newton's third law. The first is that the forces must be equal. This is what most people do remember. The second one is saying that these forces are opposite. This is also what people remember. But what people tend to forget is this last box, which is that they both act on different bodies. Right? So if this is one force which A exerts on B, the other one is what B exerts on A. So this is the most important one, right? So you can't write every action as an equal and opposite reaction. Instead, what you want to say is that if A exerts a force F on B, B exerts an equal and opposite force on A. So what this basically this improves on that definition, and this also talks about what objects do these forces act on. Next one is factors affecting thinking, braking, and stopping distance. In my opinion, this could potentially show up because thinking, braking, and stopping distances have not been asked all that much in recent years. So make sure you do know their factors. So usually these factors are really easy to talk about. For example, when we talk about thinking distance, we say that the reaction time, age, fatigue, things like that. And for braking distance, we say the friction and the tire conditions, road conditions. There's only one factor which affects both, which is speed, right? So also do make sure that you understand how you talk about the factors, because the examiner has also caught up to what you guys used to learn. So instead of just asking for factors, he'll sometimes also ask you to explain why, for example, why the braking distance would be larger if speed is higher. So how you would explain this is in this way. You would say that for the same braking force, basically, If the speed is higher, it would take longer to come to rest. Right? So you must be able to give a good, solid technical explanation for why this is so. Again, because this is distance, so you should also at the end say that in doing so, it travels more distance. These are some questions which you can have a look at. Summer 21, paper 21 and 22, they are questions 1 and 2 of each paper. I don't remember exactly what's what, but these do cover some of these factors. The logic behind the turning effects formula. So all of you at this point do know that moment is force times perpendicular distance. This perpendicular thing is what the examiner can confuse you with. So be very particular about the distances that you choose for the calculation here. And there are these two questions which are really good as far as understanding the turning effects formulas go. So you can have a look at these. Also, by the way, these are what we have done in the worksheets while our classes were going on. Next thing which I believe could make an appearance tomorrow is stability in terms of moments. And basically, let's say if I have an object which is placed here on the surface. So if I am going to rotate this object like this, so if I rotate it, when exactly does it fall off? You need to be able to explain this in terms of moments. Some people have a tendency to say this wrong statement is that they say that if the object is like this, it's stable. And if it's like this, it's not stable. This is wrong. First off, stability is basically a measure of how difficult or how easy it is for an object to fall off, right? So it does not depend on the position here. Rather, what you would explain in terms of moments here would be this, is that with the box in this orientation, the weight is going to produce an anti-clockwise moment, making it tip back down to its original position. But if it goes up to a position where the weight and hence the center of gravity come to the right of this edge, now it's going to produce a clockwise turning effect and make it fall over, right? So this is something very important and also something very fundamental, but some people still tend to forget this. Change in momentum and their reasonings is something which is really important. In one of the most recent papers, I think I have a screenshot of this down somewhere. We'll be looking at this in a moment. I think it was maybe a winter 23 paper, or maybe it was, yeah. So maybe it was winter 23 of O levels. There was this question where there was a rocket, and from the rocket, there was basically, it was expelling gas, and you had to explain in terms of momentum why the rocket was moving up. So in terms of changes in momentum, you must be able to say that if this momentum is downwards, then by the conservation of momentum, the rocket must move upwards, right? So these simple reasonings, which we have talked about in a lot of detail in class, these will be expected of you to write. Another one, which I think is one of definitely the more technical parts of this mechanics unit, is analyzing energy losses and efficiency. So with energy losses and efficiency, some of you guys might remember these sorts of questions, which are very recent, by the way. And here in such cases, you were expected to analyze why, for example, the power input is not equal to the power output, or sometimes you have to talk about why the energy is being lost or how is it being lost. So sometimes you have to identify that. So for example, in schools, you might have seen that there is a pulley system for pulling a flag. So basically, there was this one question in which a student was pulling down on this rope, and this was causing the flag to be basically raised above. And you were being asked to identify why the work done by the girl was not equal to the gain in gravitational potential energy, right? So basically, you are doing input, you are doing work, and as an output, the flag is going up, but they're saying, why is it not equal? That basically means there is some sort of loss. And the idea here was this, that there could be friction at the pulley. right? And there could also be the weight of the rope itself, which the student is pulling down. So some things like that you have to analyze. Another one which I remember that terrified a lot of students was a case of a question where there was a turbine and it was being hit by water, which was falling down from a height, and that was making the turbine turn and generating electricity. And again, the question in that case was that as the water was falling down from some height, it must have lost GPE and gained kinetic energy as a result. So why was the loss in GPE not equal to the kinetic energy of the turbine? Right. So there were also a lot of questions to this. One of those was, for example, if the water does hit the turbine, probably it's still moving afterwards, right? So that initial energy it has, it also has some final energy. So some energy is lost like this. Again, some of you guys are very, uh, you guys have a tendency to write friction in all cases, but I'm here to warn you that if you just write friction without explaining where that friction acts, so that is going to be wrong, right? Just writing a certain word like friction or air resistance without explicitly talking about how that acts, how that takes away energy, that would not suffice. So you would have to say in this case that there could be friction at the turbine, which is preventing it from turning freely. Again, another very recent question was something like this. Let me draw here, in which we had a wheelbarrow on a slope and a person was basically pushing up the wheelbarrow up a slope. So this is that wheelbarrow, and that person was pushing it up, and he was also climbing up with it. And in a in one of those last parts, the examiner was asking, why is this not very efficient as a process? So one of the easier reasons to see here is that if the purpose of this process is just to send some load up the slope, then the person himself does not have to be going all the way up the slope, right? So again, this is something which is an acquired skill. And again, I hope most of you have acquired this by now. So yeah, this is just on the spot thinking. And about pressure, the use of a barometer, how a barometer is formed, why when all of this is initially all filled up, why does this fall down? And what is then left at this point, and what heights do you use to calculate atmospheric pressure? Why do you not use water? Why do you use mercury? These are all questions that you must have a very good grip on now, right? Again, barometer is also something which I feel can come up. All right, sure. With the wheelbarrow, the idea is this, that this person had to send this load up to a certain platform. All right, Huzafa, he had to send it here at this point. So if the person just has to send the wheelbarrow and the load up here, he himself does not have to do work against his own weight, right? Because then he would have to go up. And that also basically, if you think about it practically, it exhausts him. So if you just want the load to go up, then it's not necessary for the person himself to go all the way up the slope, deposit the load here, and then come back. All right, that's what I mean here. All right, okay. So another one, this is a question from an IGCSE paper. I found that some of the IGCSE papers had really good questions related to mechanics. So this is a helicopter which is stationary at a height of 1500 meters above the ground. State two conditions necessary for equilibrium. Again, for equilibrium, you must say these two things, which is resultant moment and resultant force. Both of these is zero. So both of these are zero. All right. I'm leaving out this certain part because we also have to go forward to other ones, but something related to GPE will be done in another video, in another example. I want to come to this part right now. 1.2 shows a vertical speed time graph for a parachutist who jumps from a stationary hot air balloon. The parachutist jumps from the balloon at time t equals to 0 and reaches the ground at B. Point A indicates when the parachute opens. Right? This is stuff you are supposed to know anyway. The examiner could ask you what point A is, where does he open the parachute, and the answer is here. And how do you locate this? This is where the speed starts to decrease. So it says on 1.2, label a point on the graph where the acceleration is 0 with 1. Again, now I'm thinking about kinematics now. So this is a speed time graph. So this is Vt. How does this link to acceleration? I know gradient is acceleration. So for acceleration to be 0, this means gradient is 0, which means we are looking for a horizontal line here. So you see this at two places. You see it here, you see it here. You could have marked any one. Let's say I do this one. So this is my point 1. Acceleration is negative, means it's decelerating, right? So it's slowing down. So this is where the acceleration is negative. Acceleration is decreasing, means your graph would be getting less steep, right? It's going to be flattening out. So I can pick up a region like this. I can call this 3. Why is mercury used in barometer and not water? The simple reason for it is this, that we know that the atmospheric pressure equals to rho gh. If I use water, which is much less dense than mercury, the height of this level would be too much, right? So that's the reason here. Explain in terms of forces the changes in motion which occur from when the parachute leaves the hot air balloon until point A. So it's just talking about till when he opens the parachute. So this is for 4 marks. Please do write this in all of its detail. So the first point you should always write is that when he just jumps from this balloon, which was stationary, so initially you will say that speed is 0. So air resistance is also 0. And he falls with acceleration due to gravity. Right? Initially, when he just jumps, the only force acting on him is his weight. So he falls with acceleration due to gravity. Then you say that as he accelerates, basically this means his speed increases. So the air resistance also increases. And we know that air resistance is going to oppose his motion. So if I write it like this, the resultant force, weight minus air resistance, this equals ma. So because air resistance is going up, this entire thing is going to go down. So acceleration is also going to go down. This does not mean he decelerates. This just means he is moving with decreasing acceleration, right? So then you will say that resultant force and hence acceleration decreases. Now, if I look at this graph above, I was very obviously seeing that he does reach terminal velocity. So I would say that air resistance equals weight. And this is when resultant force and acceleration equal 0. And he reaches terminal velocity. All right. Question number 1, a girl holds a rubber ball out of a window of a tall building. Mass of the ball is given. It's dropped from rest, so you can find GPE. This is not very difficult. Girl releases the ball and it falls towards the path. The ball strikes the path and bounces vertically upwards. Speed of the ball immediately before it strikes the path is this much. After it strikes the path is this much. Calculate the kinetic energy after it strikes. Again, this is very easy. I know the speed. I know the mass. So I can use half mv square. This is what I'm more interested in, the change in momentum. So before, when it was about to strike, it was moving like this with 14 meters per second. And then it rebounds with 12 meters per second, right? When finding changes in momentum, whenever you have a change in direction, you use the sign convention. So let's do this, that I take vectors in the upward direction as positive, vectors in the downward direction as negative. And then I just use my change in momentum formula. Any change is final minus initial. So mass here was 0.2, right? Final velocity for the final momentum is upwards 12. So this is going to be positive 12 minus the initial velocity 0.2 again for mass times initial velocity. Because initial velocity was downwards, this is going to be negative 14, right? So this basically becomes 0.2 times 28, which does turn out to be Sorry, 0.2 times 26, which does turn out to be exactly 5.2 kg meter per second. Again, then once you find this out, finding the average resultant force is not a problem either. Just use this. You have 5.2 from the previous part. Divide this by 0.25, you get your answer. All right. I know I'm going fast, but it's just because I want to leave out enough time at the end so you guys can ask questions of your own. So this should be 20.8 if I'm not wrong. All right. So that's unit 1 all done and dusted. Unit 2 heat. So in my opinion, something which can be asked regarding unit 1. My formula sheet is all on my Instagram. I think some chapters are probably missing at this moment, which is space physics and nuclear physics, but everything else is on there. All right, unit 2 heat. So describing properties in terms of arrangement and movement of particles. We have done questions like this in class is, for example, if the examiner asks you to explain why a solid does not flow. And why does a liquid flow? So you know that solid has very strong intermolecular forces. Particles cannot move, so they can't flow. But liquids have slightly less strong intermolecular forces, so that would allow it to flow. Similarly, if somebody asks you why solid does not flow or why it cannot be compressed, or if somebody asks you why can gases be compressed, so with compressibility, you know that compression, if you think about it, is really bringing the molecules close to one another. So if you're talking about gases, the distances between the particles is so much that on pressing down, you can bring the molecules closer together. But with the arrangement of solids, the particles are already so close together that it's not really possible to bring them further closer to each other. Next one, absolute zero. Again, for absolute zero, it's not just sufficient that you know the temperature of absolute zero, which obviously you should know, which is minus 273 degrees Celsius or 0 Kelvin, but you must also know its understanding that this is the temperature which is associated with the minimum kinetic energy of particles. All right. So this is the minimum possible temperature, and this is because the particles here would have the least kinetic energy. Then for gas relationships, I've taught you guys this thing in this way that you really have these three things, P, V, and T, and you might be talking about any two relationships here. So if I'm talking about PV, this means T has to be constant. If I'm talking about PT, V has to be constant. If I'm talking about VT, P has to be constant, right? And then I've also made you guys write out these responses for why this happens. For example, if temperature increases, why does pressure increase? So you say particles move faster, make more frequent collisions with the walls. This must also be specified. If you do not write more frequent collisions, you will lose the mark, right? Either you can write more frequent collisions or harder collisions. So similarly, you must be able to explain all of these. Pressure temperature is without a doubt the most frequently asked one, and the next one would be PV. So, all right, there's this other thing here. Sometimes this is also asked that if you have this equation, P1 V1 equals to P2 V2, what are the assumptions? What are the conditions under which this equation holds? So one of these we just saw is that if you're talking about PV, so temperature is constant. And similarly, in all of these laws, the mass of the gas must also be constant. All right, I see we have a question. Okay. Okay, I'll try. I'll do this, Zephyr. I'll try to get this on YouTube. Variation and expansion. So for expansion, you know that gases expand the most, then liquids, then solids. And the reason for this is that the gases have the weakest intermolecular forces. So you must know the order as well as the explanation behind it. The next idea is regarding potential energies and latent heat as a concept. So with potential energies associated with gases, you should know that potential energy is basically proportional to spacing. If the spacing between the particles go up, this means that the potential energy also goes up. So for example, if I'm talking about a same temperature, then a liquid as compared to a solid at that temperature, the liquid would have more potential energy because it has more spacing. And similarly, latent heat, some people always ask me that how much of latent heat is in our syllabus. And the answer to this is you must only know this in terms of the work done against the intermolecular forces. But it's not going to be asked like this that, all right, tell us what latent heat is. It will be asked this way that you will often be asked to explain this in terms of state changes, in terms of some heating or cooling curve which is given to you. And an explanation for this is, an example for this is going to be given below. Next, you have the molecular explanation for evaporation. This is also pretty important stuff. I think this can seriously come in your paper tomorrow, which is to explain how evaporation happens on a molecular level, which is how those more energetic particles basically go away, and all of these factors, how they're affected by them. That is important. The differences between evaporation and boiling, those are important. The next idea is about practical heating and cooling curves. So in reality, if I make a cooling curve is not like this, rather it's like this, right? So you must be able to explain why this shape is actually a curve. And we will look at this in a question below. The idea here, what makes the shape go from this to this in reality, is the idea that the temperature difference is proportional to the rate of thermal energy transfer, right? So initially, if something is very hot, it's going to initially cool down really fast, but with time, this slows down because the temperature difference goes down. This idea has also been assessed in a lot of ATPs. Convection and density changes. Again, I think that conduction has been asked somewhat. Radiation has also been asked. So I think this time out, convection will be asked. Also, do focus on the examiner's words. Whenever they want you to write about convection, they will use a word like this, how all of the water or all of the air is heated up. Or they may use a word like this, that uh, how is heat transferred upwards, right? So these two words are your cues to understand that this is convection that the examiner wants you to write about. Next step about household insulation is you need to understand the idea of air pockets, how that can help reduce conduction and convection, but it doesn't really reduce radiation because that can take place in a vacuum as well. So then there's this question, in my opinion, one of the hardest questions ever related to thermal properties. Yes, in my opinion, yes. Thermal properties is a pretty major thing. Now it's nothing to be taken lightly. So this says a small glass measuring cylinder of oil is placed inside a freezer where the temperature is constantly negative 18. 9.1 shows how the temperature of oil varies with time. Then it says in 9.1, it says that it takes 700 seconds for the temperature to go from 20 to 10, right? This takes 700 seconds. But then it says it takes 1900 seconds from the same 10 degrees Celsius drop from 0 to negative 10. So why does this take more time? So this is basically asking about this idea, which is that why is this not a straight line? Because if this was a straight line, then every 10 degrees Celsius drop would take the same time. But initially it cools down faster, later it cools down slower. So this is the idea regarding temperature difference. So the answer to this one is that initially oil is much hotter. So the temperature difference with the freezer is greater. And as the oil starts to cool down, the temperature difference also goes down. So the rate at which it cools decreases, right? How can you remember this in terms of a simple example? Is that, for example, if you go out and play and if you come back into an air conditioned room, you feel the coldest first because the temperature difference with the room is the greatest. But afterwards, you don't feel as cold because the temperature difference has gone down. Explain what happens to the molecules of oil and explain what happens to the level of oil in the glass measuring cylinder as the temperature decreases from 20 to 0. Keep in mind, this is not a state change, right? It's talking about 20 to 0. So you just say that the particles, because they are now cooler, they have less kinetic energy, so they move slower and hence they come closer together. So the level of the oil in the glass measuring cylinder decreases. Determine the melting point. So the melting point is always a horizontal line. So this is -10. And the next one asks, explain in terms of molecules why the temperature of oil does not change between 3600 and 10800 seconds. So this is talking about the state change. So molecules come closer because this is freezing now, right? The melting and the freezing point are the same. So they come closer and intermolecular forces basically increase. So bonds are now formed. And since spacing is reduced, its potential energy now decreases. So it's now going to release that energy, and this is lost as latent heat from the oil to the freezer. This is what you were supposed to write here. Part D is not in our syllabus. Part E is the graph in 9.1 is steeper before the horizontal section than it is after. Use this to compare the specific heat capacity of oil in the liquid and solid states. So it says this is steeper. This is not as steep. So this means the temperature here falls faster as compared to here. If I think about the specific heat capacity equation, if the temperature here in this part, if this is rising or falling faster, this means the specific heat capacity is less because it's really, it's losing energy more frequently, right? So its specific heat capacity in this case goes down. Yes, latent heat of vaporization and fusion is not in your syllabus anymore. Not even specific latent heat. It's just latent heat and what it means in terms of work done in molecules. Again, a question like this we have done, so I'm just going to skim over this. I'm not going to write out an answer. So this is a syringe in which air is trapped. This is the reference, summer 22. So again, a very recent paper. It says explain how air molecules create a pressure. Now, I've seen a lot of students make this mistake that they write it like this, that they start to talk about the plunger either being pressed in and how that causes less volume and more pressure. But that's not really what the question is asking. It just wants you to talk about how even is there a pressure in the first place. So the first thing here that you talk about is random motion of molecules, which means that they are always moving. And in doing so, they collide with the walls of the container. And then the last thing you say is that because of their collisions, now it's your call. Sometimes the examiner may want you to involve momentum here, but if it's not, you can't, you don't really have to do this. So you could either say that because of a change in momentum, there's a resultant force, or you could just straight up say that there is a force here which leads to pressure. All right. So this is what the question was asking. Part C was also slightly tricky because the P1 V1 equation, the setup here is slightly more technical. It was told that a 10 Newton weight is placed on top of the plunger and the plunger moves down slowly and the temperature does not change. This word is your cue that you have to use P1 V1 equals to P2 V2. Before the weight is placed, you know the pressure volume, you know the cross-sectional area, and you are supposed to find the pressure of air in the syringe after the plunger stops moving. So with the weight on top here, the idea is that whatever this pressure is would also be the pressure exerted by the air if the plunger is not moving, right? If there was a imbalance of pressure, maybe if the air had a greater pressure, the plunger would move out. If maybe the air had less pressure, the plunger would move in. But if it's not moving, this means that their pressures are equal. So the first thing that you have to do in this part to find the pressure of the air in the syringe after the plunger stops moving. So you are really finding the new pressure here. This would be simply F over A. So you have F, you have A, you divide and you get this new pressure. And then using this in the next part, you find P1 V1 equals to P2 V2. That's how you find the new volume here. All right. So this is how this part was supposed to be done. All right, now on to unit 3, which is waves. So definition of wave terms, please make sure that you have this really solid. For example, if somebody asks you to define time period, so you can say that this is the time it takes for a wave to completely pass a point. And then, for example, if somebody asks you to find wavelength, so how do you define wavelength? So you can say it's the shortest distance between two consecutive crests, or you can use the word wavefronts as well. Similarly, if somebody asks you to define frequency, so for frequency, you can say that this is the number of waves or the number of crests that pass a point in a time period, right? So this is just stuff that you are supposed to know how to define. This is really important stuff, and people needlessly lose marks over this. The next one, which I as a student relate to the most because I often had troubles with this, is when you analyze wave speeds, when you talk about this equation V equals F lambda, how does it actually even work? Because sometimes you see this that if you are basically moving a rope up and down, then you see that if you wave it up and down twice as fast, so if you have increased the frequency, you see this, right? If it's more frequent, so you see more waves. And you can see that now the wavelength has decreased as a result of the increased frequency, right? But sometimes then, when we talk about a wave, for example, a water wave in a ripple tank moving from deep to shallow water, we say that the speed does not change. So what's at play here? What are we missing? The idea here is that the speed of a wave is only decided by the medium in which it travels. So if we are in a certain medium, the speed of the wave will always be the same. If I am in deep water and if I increase the frequency of vibration, the wavelength will decrease. But when I go from a deep to a shallow medium, this classifies as two different media. So the wave speed can then change, right? Also, a mnemonic that I use for water waves is this. I have shared it with you guys before, is SH for shallow, SH for shorter, which is this idea that in shallower water, the wavelength, the wavelength is also shorter, right? So the frequency does not change. The frequency does not change because it's decided by what produces the wave, but the wavelength does change, and ultimately the speed also changes. Wavefronts drawing is also something which definitely can come in to your exam. Diffraction has been asked in the most recent paper. It was also asked in one of the papers in 2023. So in my opinion, diffraction will not come in, but you can definitely have a wavefront drawing question for refraction. Right, so this can definitely come in. Formulas for refractive index. A lot of people do remember sine I over sine R, which I write as this: sine of angle in air over sine of angle in the medium. But a lot of people do forget this one, which is C over V, which is that refractive index is a ratio of the speed of light in air divided by the speed of light in any other medium that I'm talking about. And it's actually the differences in its speed which makes it bend, right? So do remember this as well. This has been, the examiner knows that students is slacking off on this part of the formula. So he is asking this a lot. Optical fibers, another thing that I suppose could come in. The advantages, disadvantages of optical fibers, and what kind of wave is used in optical fibers, the answer to which is infrared as a wave is what is used. And what's the advantage of faster data communication, more secure, lighter, And these are all advantages, more bandwidth, right? Ray diagrams for lenses, cases, and examples. This is also super important. It's been asked in the 23 paper. It's also been asked recently in the March 24 paper, which was on the YouTube channel. So ray diagrams and how you relate those to the number of examples. If I just show you guys quickly here, I don't want to spend too much time here. So these are the cases for lens ray diagrams that we did. Case one, object at infinity, and then its applications. Case two, the object beyond 2f, its applications. Case three, with the object exactly at 2f, which is the only case where you have a same size object. Case four, with the object between f and 2f, which is a real inverted magnified image. Case five is the object at the focus. So this produces no image. And the only one which produces a virtual image is when you have an object placed between O and F. This is where the object is here, right? And then because of the virtual image formation, when we take those rays back as dotted lines, you have an image formed. This is the only one in which you have a virtual same side as the object and an upright image formed. In the case of all real images here, all the images were inverted if you see, right? All images are inverted here. So the only case where you have a virtual upright and the same side as the object image formed is when the object is placed between O and F. And the application for that is in a magnifying glass and in a VR, in a virtual headset. So let's go back here and have a look at some of these questions. And the explanation for dispersion is also something I feel, because the examiner knows that students are slacking off on this, it could ask for an explanation of dispersion, which is why red light bends less. Why does violet light bend more? And the reason is that red light slows down less, which also causes it to bend less. What bends more, what deviates more is because it slows down more, right? This is exactly the idea of refraction. And why does white light not just separate in air? Is because in air, everything has the same speed, all colors. But in a glass prism, all the colors have different speeds. So all colors have different speeds in light. Please do make sure you have a really solid grip on this. I have a really strong gut feeling that this can come in tomorrow. Another thing related to lenses, which has not been asked for some time, maybe it makes a surprise appearance tomorrow, is long and short sightedness. So for long sightedness, what's the idea? Is that the rays basically converge at a long distance behind the retina, right? So to correct this, because it's not converging here, this is where it should converge. So you use a lens which focuses the rays in more. So you use a converging lens to correct long-sightedness. How do you remember what long-sightedness is? Is that this is the natural lens in your eye. In long-sightedness, the rays converge at a long distance from the lens. In short-sightedness, it meets before. It maybe meets somewhere like here. So you can see that then in that case, it meets at a short distance from the lens. So in that case, you want to spread it out more so that it meets later, in which case you use a diverging lens. Applications of ultrasound. So this is also pretty important stuff for MCQs as well as this. If it doesn't come tomorrow, then it will definitely come in MCQs. So applications of ultrasound, which is that fetal scanning. For fetal scanning, do make sure that you know that the reflected ultrasound is what forms the image. right? Similarly, the idea of sonar methods, how you estimate depths and whatnot. Jewelry cleaning. So when you basically have a piece of jewelry immersed in a solvent, and when the ultrasound strikes it, makes the dirt particles vibrate and move, and then they get dislodged, and that is how jewelry cleaning works. So you do need to know in that in all of the detail. Yeah, prenatal scanning and fetal scanning are pretty much the same thing. Yes. Production of sound, again, something that I see a lot of students needlessly again losing marks here on is how sound is produced. So, sound is always produced by some sort of vibrations, and those vibrations basically lead to compressions and rarefactions. And then you must also know what each of these are. So for example, if right now I'm speaking, right? So let's imagine I have a lot of particles in front of me, which are just floating in the air. So if I'm speaking, my voice and the wind, which it basically throws out, this makes some particles come closer together, which is compressions. So places where air particles are closer together, leading to a higher air pressure, is compressions. Similarly, because these movements are alternating, rarefactions are places where the air particles are further apart, leading to a lower air pressure than the average value, right? Also, some people do forget to say that these sound waves would also vibrate back and forth in the same direction as the movement of sound, because again, sound is a longitudinal wave. That's how those particles move. Now, this is another question. Just hydrate myself. This is a question which is on dispersion in a way and also on refraction. Two parallel rays of light, one red, one blue, enter. 3.1 shows both rays of light before they enter. Blue ray is also shown incident on a different side of the prism after passing through the prism. On 4.1, mark an angle label of incidence and the angle of refraction for blue light. And the examiner has been as nice as to make the normal for you and give you a hint already. Always know that all angles are marked with respect to the normal. So this would be the angle of incidence. This would be the angle of refraction. And then it says on 4.1, continue the path of the blue light after it strikes the left side of the prism. So we were told this is the critical angle. And the critical angle is the angle of incidence, which causes the angle of refraction to be 90. So after this angle becomes 90. So it's totally lying on top of the edge of the glass block. Then part 3, refractive index of glass for red light is smaller than the refractive index for blue light. The refractive index is just a measure of bending. So the idea is that the red light would not quite bend as much as the blue light. So I'm going to make this definitely more gentle here. And also in this case, it would not bend as much. So like this is what I would make it to be, right? So less dense to more dense, it bends towards the normal. More dense to less dense, it bends away from the normal. All right, critical angle calculations. This is pretty easy stuff. This is one of the more recent papers that we've also done in our sessions, not too far back. Isn't violet light supposed to be the with the least? Violet light bends the most, right? Violet light bends the most. So yeah, it deviates the most basically. So it would have a larger refractive index. All right, the VR question, this was also on lens formation. So the display is the object for the lens. The lens acts as a magnifying glass and forms a virtual image. Describe where the display must be positioned relative to the focal length of the lens for the lens to act as a magnifying glass. So you know that in that case, it must be between O and F, right? So it must be between the optical center and the principal focus. So it must be within the focal length. So within focal length. explain how a virtual image is formed. Again, this is also a question which has been asked somewhat recently, how a virtual image is. And you just say this, that the rays just appear to come from a point. So it's not a real image, can't be captured on a screen. The rays just appear to come from a point, but it's not actually coming from there. So an arrow on the display is 3.4 centimeter from the lens. Virtual image of the arrow is 22 cm from the lens. So this is 22, this is 3.4. 6.3 shows the arrow, the lens, and the virtual image of the arrow eye drawn on a grid with a scale of 1:2. All right. So on 6.3, draw a ray diagram to show the formation of the virtual image eye. So here you use your lens plotting rules. So one of these is that if you have a ray which goes exactly through the optical center, that is not deviated. So that's what I'm trying to do with this ray. And the other one is this. I know that if this ray is going parallel to the principal axis here, so it would be refracted in a way that it would pass through the focal length, right? But now I don't know what this focal length, where this would be, right? I don't know how to take this. But I do know this, that if I take this ray back as dotted lines, back to meet this tip, so it would meet here. So I can use this sort of reverse engineering to see that if I make it like this is how my ray should be, right? This was the idea that was at play in this question. Always make sure that the lines you take back behind the lens, they should be drawn as dotted lines. Obviously, I can't do that because of the software I'm using, but you should take care to do that. So then you would just measure this distance, and this would be the focal length. Because of that ray rule, that a ray parallel to the principal axis gets refracted through the principal focus. So this is your focal length. All right. Unit 4, electricity and magnetism. So plotting of magnetic electric field lines. This is obviously a very, very important thing. Again, it's sort of easy, but people needlessly do lose marks over it, as we'll see in a while. For example, if you are supposed to make an electric field line due to a current, right? So let's say this current goes up like this. So let's say I have it like this. And because the current is coming out, it's coming towards me, I make a dot here, right? So the current is coming out. So let me write current out of the paper. Now, if in this case, I want to make the magnetic field lines because of it, there are some things that I must take care of. First off, you know that because this is out of the paper, I'll use the right hand grip rule, and the direction of curl of my four fingers would give me the direction. So I can see it's anti-clockwise. And I also know that this would be concentric circles. But with concentric circles, the mistake that people make is that they do not show an increasing spacing. So if this one is this distance apart, if it's this distance apart, the other one must be a larger distance apart. And the next one should be even further apart. If at any stage the examiner feels that the spacing is the same, for example, if I make it like this, the spacing is approximately the same, I would lose marks. So make it as dramatic as you can. Now this is very obvious that the spacing is, yes, increasing. And then I just add the directions to this here. It should be like this, this, and this. All right. But the focal length, I have not marked this here because I'm not sure that my answer would be exactly accurate because of the scale of the drawing. But this is what it is. Small f, focal length. This is it. All right, Saad? All right, applications of electromagnets. This is also pretty important stuff. So regarding a loudspeaker, the moving cone loudspeaker, how it works, the idea of a reed relay, right? And just a relay and how that works, that is really important. I think that could appear tomorrow. Sources in series versus in parallel, you need to know the advantages, disadvantages. For sources in series, the advantage is that these can give rise to a greater EMF. And the idea of parallel is that this lasts longer. Aside from the obvious advantage for parallel, which you also write in components, which is that if one source runs out, the other one can fill in for it. A potential divider using thermistors, LDRs, is also something that I feel is definitely going to be tested tomorrow. The voltage divider rule, kilowatt hour, again, something which has a really high chance of being tested tomorrow. With the kilowatt hour, you are supposed to know its definition. First off, it's the energy because it's power multiplied by time. So energy, 1 kilowatt hour is defined like this. So this is the energy used by one appliance, by a 1 kilowatt appliance or a device when used for 1 hour. And the only thing, literally the only thing you need to take care of when using this formula is to make sure that your power is in kilowatts and your time is in hours. And then you just multiply them together. That's all this is. Why are fuses and circuit breakers connected in the live wire? So this is in the context of a metal casing. Because if you do not connect it to a live wire, and instead if you connect it to a neutral wire, the circuit will be broken, but the casing could still be live, right? So that's why you do it in the live wire so that the casing is not live. Factors affecting the induced EMF of a AC generator and of anything in general. So the idea is that you have, if I'm talking about an AC generator, so definitely the rate of rotation, this affects it, and the magnetic field strength, right? And the turns as well, if you're talking about a coil. But do remember that you should treat this certain factor with a lot of respect and a lot of special consideration, because this is the only factor which also increases the amplitude and the frequency of the induced EMF, right? If the rotation gets faster, so the amplitude also obviously increases by Faraday's law, that more field lines are cut, but the frequency also goes up. Uses of split rings and brushes in the DC motor. This is also really important. We've done a recent paper in which this was discussed, which is that the split ring basically reverses the direction of current in each half cycle, and it makes the coil keep turning in the same direction. And brushes are just used as a electrical contact with the external circuit. And sometimes you can also write this, the examiner does mark it, which is that the brushes reduce friction of the rings with the wires, right? High voltage transmission. So in terms of the formulas, and again, this is on my Insta, which is that why high voltage transmission is what we use is because if we think about P equals VI, a higher voltage leads to a lower current, and by P equals to I square R leads to less power losses. So now let's say we are talking about this question, and let's say you did not see what was written above. How would you conclude whether this is a generator or if this is a, what do you call it? If this is a generator or a DC motor? Because this is also something which has been started to be asked recently. What is this? All right, good job. Good job, Saad, Zafar. The idea is that yes, it does have slip rings, right? These are slip rings. What the DC motor has are split rings. And if you keep the split in mind, it really has a sort of a cut in the middle here and in here. So it's basically like two halves. It's like this. For a DC motor, you have these two rings, and those rings are rotating with the coil, and that's how that current is reversed. But in this case, you have a whole ring, right? So this is a AC generator. Good job. This is exactly what was also written. I just wanted you guys to think about it for yourself. So P is your carbon brush, Q is your slip ring, right? So explain the purpose of P and Q. We've talked about this. So the Q, that is just basically ensuring the electrical contact with the outer part of the circuit, and it just enables that to be transmitted outwards to some external circuit. For some reason, I also see that people get stuck with oscilloscopes. I just wanted to do one comprehensive example to tell you guys how this works. Again, never ever memorize the formulas for the oscilloscope, just work with the units. You know, this is the time base setting, so in some way this would be related to time. The only idea is that if you want to find the time period, you take the time base, in this case, which is 2 milliseconds per centimeter, and you multiply by the number of divisions, by the number of centimeters in which one wave forms. If I look here, so this is 1, 2, 3, 4, in which one wave forms. This is 4 centimeters. If you are doing this correctly, you will automatically see this happening, that the units cancel out. And the unit you get for the time period is 8 milliseconds. And then if the frequency is asked, you just do 1 over 8 milliseconds and you get the frequency as well. You do exactly the same thing for the Y gain as well. For the Y gain, because this is Y, so this is vertical, you know that this somehow relates to the amplitude. In this part, we are asked the max value of the EMF, so the peak value, which is this. So for the amplitude, which is the max value, I would take the Y gain, which is 5 volts per centimeter. And now I would multiply by the vertical divisions corresponding to the amplitude. Now, again, if I see here 1, 2, 3.5, so 3.5 centimeters, again, you see these canceling out, and the amplitude is whatever this would turn out to be. All right. So this is how you should aim to work with oscilloscopes. All right, so this is a very detailed question, and I'm pretty sure we did do this in our classes throughout the year. A student connects a battery to two resistors. The circuit diagram is shown. Potential difference across the 40 ohm resistor is 9.6 volts. So this is 9.6 volts. State what is meant by potential difference across a resistor. How I define a potential difference is in terms of work done. So I say work done, but this is by a unit charge in moving through a component. Some people also like to do it in terms of energy transfer. I personally prefer this more. So if you say work done by a charge, you get 1 mark, and for saying that unit word, you get the other mark. Calculate the current. This is also not difficult. If I know the current, if I know the voltage, if I know the resistance, I can find this out. So I get the current in the 40 ohms resistor, and then I am expected to find the EMF of the battery. Again, the nice thing about electricity, at least the cool thing, is that there are more than one ways to do this. You could have found out some current here. You can think about this as a total resistance, right? You can think about this as a total resistance and use the calculations according to this. So I, and then total resistance would be 50 ohms, and you multiply V equals IR and you get the EMF. Or an easier way to do this, maybe an easier, but definitely a cooler way to do this, is that if 40 ohms has a 9.6 volts drop, something that has 1/4 the resistance would also have 1/4 of the voltage drop, right? So 9.6 over 4, which turns out to be 2.4, is what the drop would be across 10. And then you add both of these because of the voltage division argument. which is that whatever the potential differences are must equal the EMF of the source, right? In both cases, you should be getting an answer of 12 volts. Another thing, which is the choice of analog meters. So you must take a meter in which the reading you want to measure lies smack in the middle of the range. So for example, here the PD, the potential difference that we wanted to measure is 9.6, right? We have 0 to 2, 0 to 20, 0 to 200. We would not do 0 to 2, obviously, because 9.6 can't come up in that range. 0 to 200, this would mean that there would be a very, very small deflection for 9.6. And the last one is that if you do 0 to 20, so this is pretty close to 10, so you would get a really noticeable deflection. So you do 0 to 20 here. Power ratings. So you find the power the student has available, two 10 ohm resistors with power ratings of half P and 2P. So just why a power rating of half P would not be suitable is because if it can only tolerate a max power of half P, if you give it more power, it's just going to blow. This is what I am more concerned about, and this part is why I did take this question to do, which is that you are told that to that resistor, you add a resistor R in parallel. And you need to talk about what happens to these different quantities, and you also need to explain. So the first thing you must understand at this point is because this resistor is added in parallel, this resistance goes down. No matter if this resistor R is 40 or greater than 40 or less than 40, whenever you have an existing resistor, you put in another resistor in parallel, this resistance will go down. All right. So I'm already given current in 10 ohm resistor increases. It should. Because if this resistance goes down, the total resistance also goes down. So the current goes up. So I'll say total resistance decreases. This is why current increases. Then I'm asked the PD across the 10 ohm resistor. Again, there are more than one ways to do it. One is the voltage divider argument. This other one is simple V equals IR. Because I know the current goes up, so if I think about this in terms of V equals to IR, its R is the same, but I has gone up. So I would say this also increases. And the reason would be that a greater current basically leads to a greater PD, right? It has a more voltage drop across it now. The last one across the 40 ohms resistor. Now for the 40 ohms resistor, how would you talk about this? You want to talk about the potential difference. So one of those ways is to talk about it like this, that if this voltage goes up, let's write like this. So this is some voltage V1, which appears here. This is some voltage V2, which appears across these two. And I know that because of voltage division, V1 plus V2 must always equal the EMF of the battery. So if V1 is going up, I can say that V2 has to go down, right? This is one way. Another way to talk about this is this, that because this resistance basically becomes a smaller portion of the overall resistance. So because of the direct proportion by V equals to IR, this voltage would also go down. These are the two possible explanations for this part. So I would say this decreases. And the reason is that since voltage, let's write like this. Since the voltage across the 10 goes up, voltage here must go down so that the total remains same, because the total is the EMF. This is the question that I am predicting, which comes in tomorrow, which is a relay. So the working of a relay, you should know the advantage of using a relay, you should know. So I explained why the motor switch is on when the switch S is closed. So when the switch S is closed, you can see that the current would flow through the coil of wire, which would magnetize the core, and the core would pull the iron armature toward itself. This would close the contacts, and switch on the motor, right? Explain why the core is made of iron rather than steel. So I know iron is a temporary magnet, which allows me to turn it on and switch it off on command. A student suggests that the motor can be turned on and off without a relay. He suggests connecting the main switch to a simple switch in series with the motor. Suggests one reason why in some situations using the relay is better. This is the advantage of using relays. The idea is that if I use a relay, I can use a small current to switch on and to control a much larger circuit. So it's better for safety as well, right? It reduces the risks of fatal electrocution because I'm working with a much smaller current here as compared to the current that would flow here. So this is something else that you guys can have a look at. So in this one, you are supposed to draw the magnetic field inside and outside the coil. If you use the right hand grip rule, you will find out this is north because of your hand curling like this. So it points in this way. So this is my north. This is my south. So I make the field lines here. They must be inside as well. And inside the spacing should be constant. I should actually draw maybe a few more like this. And then you just make some of these loops. And this would be like this. And then this one would be like this. Right? So this is how you make the field pattern in this case. This is something related to induced EMF. Describe how a permanent magnet produces a large reading. So a large reading would be because of a large voltage, a large induced EMF. So you can either use a big magnet, a stronger magnet, and you move it really fast. Explain why a current is produced in one. So you can say that the magnetic field is cut by the field lines, which causes an induced EMF. This is exactly Faraday's law. Or you can say there's a change in the magnetic field or the magnetic flux in the coil. Either or works perfectly fine. All right, on to Unit 5, nuclear physics. So alpha scattering is something which did come in into the IGCSE March 24 paper. So I hope you guys now know exactly what observations correspond to what conclusions. So that's something that could be asked. Nuclear fusion. Again, I have a really, really strong feeling that nuclear fusion could come in. Is because nuclear fission has come in winter, and it was asked in a lot of detail. And nuclear fusion has not been asked for quite some time. So I feel that nuclear fusion could be asked in this one. So with nuclear fusion, you need to know this equation, obviously. The two hydrogen isotopes fusing together to give helium and a neutron. And you must also know what are the requirements of this. Why does it need a high temperature? Is to bring those nuclei closer together to overcome their forces of repulsion. Isotopes, this is pretty easy stuff, comes in almost every other session. So this can also be there. Randomness and spontaneity is also something I feel that can come in. So you might be asked the meanings of each of these. So randomness means you cannot predict when a certain nucleus will decay. And spontaneity means this is not affected by external conditions. Half-life problems, which also have to be corrected for background radiation. If you guys remember, this was there in the March 24 paper. It was quite a technical question. And I will show you guys that as well. Effect on the nucleus of beta decay. So now you need to understand this idea. This was also asked, by the way, in the March 24 paper, which is that if you have an electron being emitted, so in the nucleus, there are no electrons. So where does this electron come from? So the idea is that this happens when a proton converts, all right, no, I've messed this up. The proton is on this side. when a neutron turns into a proton. All right. I have never memorized this. I just use the conservation of nucleon number, conservation of proton number, which is why first I put the proton here, but then I identified that this must cancel out for this to be zero. Applications with respect to ionization, penetration, and half-life. This is also something which will be asked again. This has not been asked for quite some time, so it will definitely be asked either in the MCQs or in the structured questions this year. So for example, if we talk about PET scans, where you have a tracer in the human body and that emits radiation, and this is being detected by some machine outside and it's using it to construct an image. What type of radiation do you use in that? This is a question that has been asked in MCQs. The answer to this is gamma. And the reason is this because it is very penetrating. It's not very ionizing. This is exactly what we want because ionizing effects of radiation can have a lot of adverse effects such as cell death, mutation, cancer, and whatnot. So we don't want it to be ionizing. We want it to be very penetrating so that it goes from our body outside to that detector. And how should the half-life of this be? So because we want it to just be there for a small time while we're doing the scan, the half-life should be in a few hours. It shouldn't be something in like years or something. It should be only a few hours or only a few minutes so that it just gets done with it while we're doing the scan. In comparison to this, let's say you are using a radioactive isotope for measuring thickness, measuring the thickness of a certain metal. Now, what do you want to happen in this case? Again, ionizing we don't really care for because the metal can't really die or something. But we would want for measuring thickness, we would want it to be not very penetrating because what we do is that we send out these different radiations, and on the other hand, we monitor those and we want to see how much of the radiation actually reaches. So what we use in this case most of the time is beta. And the half-life of this must be very long, must be a few years so that it just doesn't run out immediately while we're doing that production process. We want it to have a long life. A ionizing radiation causes cancer and those stuff. A penetrating radiation does not have those effects. So just which type of radiation is the most ionizing, which is deflected most by a magnetic field? The answer is beta because it has a uh, large charge and a small mass. Explain how the readings show that the source emits beta and gamma. It emits beta because when I place the 5 mm thick metal, so if the reading drops by 800 to 200, this is because of beta. But if I still have a reading of 200, that means it is going through the metal. So that is gamma, right? That's what you need to explain here. State why the readings cannot be used to show that the source emits alpha particles. So that is because the alpha particles are very less penetrating. So these would be deflected, these would be totally blocked by this, and also because of the fact that they have a really small range in air. It's only like 3 or 4 centimeters. So it would just get ionized in air, it would just finish out there. So that's the answer to this. How can a radioactive source be moved safely? So for moving safely, you store it in a lead box, you use forceps, you minimize the time of exposure. So all of those things that we always write about, you can still write. Yes, tongs, forceps, same thing. 9.1 shows some properties and values for alpha, beta, gamma. Complete table 9.1. Again, this is, yeah, so this is also a really recent paper. I am more concerned, actually, let's do the table as well. So for beta, the number of protons is 0. Number of neutrons is 0, gamma, this is 0 as well. For alpha, because this is a helium nucleus 4, 2, right? So it has 4 nucleons. If 2 are protons, then the other 2 must be neutrons. The charge on a beta particle would be negative, and it's negative of the charge of it's basically an electron, so that's the charge here. Negative 1.6 into 10 to the negative 19. This is 0. And start by thin sheet of paper, thin sheet of aluminum. This is by very thick lid. So just how beta decay changes the nucleus of an atom. We just did this. A neutron turns into a proton, right? Next one, C. This is what I want to talk about. So a radiation detector is used in a lab, detects a background rate of 30. It detects this always. Radioactive source is placed in front of the detector. Initial reading is 550. So in this 550, the 30 is already in there, right? So the first thing you must identify is that you must subtract this. So 520 is only the radiation because of the detector. Why do I need to do this is because with time, the half-life is given of the source. The background radiation will always be giving me 30. What will be having is the counts from the source. Always in terms of a half-life question, think about how many half-lives have elapsed. So if one half-life is 70, if one half-life is 25 minutes, 75 minutes mean three half-lives. So I have 520. And now this is going to halve three times. So the number of arrows are the number of half-lives. Once it halves, it goes down to 260. Then it halves, it goes down to 130. And then another one. So I have three arrows, three half-lives now. This goes down to 65. Again, 65 is just because of the source. So to add the background radiation back again, the answer here would be 95 counts per minute. Right? So this was a very technical question. It's also for 4 marks. So it's a lot of marks. Safety precautions again. Again, this is what we just talked about. What would you use? Explanation, what would be the half-life? Right? So we've just talked about this. Let's go on to space physics. So space physics, what I feel could come in, especially in the MCQs or in the structured questions, is how gravitational potential energy and kinetic energy varies in orbits, where the thing which is orbiting is closer to a planet. So the gravitational potential energy is less. So the kinetic energy must be more. So it must be traveling faster. All the differences between comets and asteroids in terms of their shape, in terms of their composition, in terms of what has a tail, what does not have a tail. These are all covered in great detail in my YouTube channel. So if you feel like you're lacking here, check that out. Force required for orbit. So it's a gravitational force which provides the force necessary for circular motion, and how it basically changes for each planet. So for the planets which are further out, we know that because the gravitational field strength of the sun is weaker there, the force is also less there. So it causes it to travel slow, which is why the time for orbit decreases as we go out. Stability of stars in terms of the nuclear fusion reaction that we just looked at, how that takes place. In IGCSE and in our board as well, to some extent, you also have to explain this in terms of forces. So what we say is that the inward force of gravitational attraction, this equals the outward force due to the high temperature in the core. So when a star is stable, both of these forces are balanced. Differences between the deaths of medium and large stars. So for example, if you're talking about a medium star, you have a planetary nebula, white dwarf, black dwarf. And for a large star, you have the supernova and then the black hole and then the neutron star and all of that stuff. So you do need to know that. Again, light year calculations, in my opinion, are definitely going to come in your paper tomorrow, because it has not been asked for quite some time now. So light years, you must know that this is the distance traveled by light if it's traveled allowed to travel for 1 year. IGCSE students do need to know by heart that 1 light year is 9.5 into 10 to the 15 meters. O-level students are not expected to know this. They should just be able to calculate this and show how this is calculated uh, in real time. Redshift and Big Bang. So how Redshift provides an evidence for the Big Bang theory, this is also something which I feel is going to be tested tomorrow. If you're talking about IGCSE students, so they might also be asked to explain how cosmic microwave background radiation provides an evidence for Big Bang. Again, this is also covered in my video. So it's really short videos. You can just skip to the end and look at what the solution to this one is. Accretion model is something that I feel has never been as tested in IGCSE, especially in paper twos, could be tested then. And seasons is also something which has not been tested ever since space physics was included in IGCSE. The last two, and whatever is written in purple on this slide is IGCSE only content, right? State what is meant by light year, so distance traveled by light in 1 year. Approximate diameter of the Milky Way galaxy in terms of light years, this is 100,000 light years. Then these stages, again, these questions we have done previously. So neutron star, black hole, and the nebula, all of this stuff we have done. And state the stage in the life cycle of a star where heavy elements are formed. This is the supernova where you have elements heavier than carbon being formed. This is what I'm talking about, which is that how, for example, in this case, how does redshift support the Big Bang theory? So there are really a few steps that you need to talk about, a few reasons, and you go exactly in this order. So you say that most galaxies, so light from most galaxies is redshifted from most galaxies is redshifted. And what another observation is that galaxies further away have light which is even more redshifted. So what this means is that the galaxies which are further away are also moving further away. So going back in time, all matter must have been at a single point. Right, so that's what the reasoning is in short here. All right, so that's this. This is another IGCSE paper. You are supposed to state the name of a planet X, which if you look here, so this is so 3 planets in the solar system, and you are given some data according to this. Now here the cool thing is that Earth and Jupiter, you know that these are very far apart when we talk about the naming, right? MVEM, JSUN, right? So Earth, and then there's Mars, and then there's this. So how do you deduce what this planet X is? So if you look at here, the distance from the sun is closer, right? So MVE, so this must be Venus. The orbital period is also less, so it must be closer, right? So this is Venus then. Describe the relationship between the mass of a planet and the gravitational field strength. So you can see that as the mass is greater, the gravitational field strength is also unanimously greater. Explain why distance from the sun is an average value. Good question. Which is that orbits are never circular, they are elliptical. So we take the average value, the average orbital radius. And this question is also very easy. It's just the usage of this formula, V equals to 2 pi r over T. So IGCSE questions do have like good space physics practice material if you feel you're lacking in those. So now for the moment you all have been waiting for. So this is my paper prediction. It's not really a guess paper. It's more like what I feel could be assessed in one way or another. So question number 1, in my opinion, because thinking breaking stopping distances have not been asked from 22, they weren't asked in all of 23, they were just asked in MCQs. So I feel like this is what the first question could be. And with a case, for example, where a vehicle is braking and coming to rest, there could also be related parts on momentum, impulse, and force, right? That's what I feel it could be. And maybe you could have a small question on barometer and the kinetic model of matter as a small question too. So maybe for 5 or 6 marks. But this one, the first one, I do expect it to be a heavy question. Next, I expect energy conversions, some idea on renewable resources, and a suggest and analyze part, as we were just looking at, for example, the wheelbarrow question or pulling up the flag question. And there could be a part on terminal velocity, how it's reached, and a resistance as well in the question number 2. Third, gas laws, relationships, absolute zero. I feel like this can come in, and also P1 V1 equals P2 V2. This is also what I feel can come in. Question number 4, a practical heating curve. Again, I have my money on this, that this is going to come in. The latent heat explanation, because what I just showed you the question from, that was 2020, and it's been quite some time to 2020. So I feel that that could come in. Specific heat capacity calculations, and some cases in which you are expected to predict methods of heat transfer and ideas of insulation. This could be a question, and maybe both of these could be merged in a single big 15-mark question. Defining wave terms, first one, this could be like the first part A of that question, V equals to F lambda. Then you could have refraction is what I think is going to appear tomorrow, how that affects speed, how that affects frequency, how that affects wavelength, and the drawing of those wavefronts. Reflection ray diagrams, the two ways in which you draw ray diagrams related to reflection, those have also not been asked for quite some time. The properties of images which are formed by a plane mirror, critical angle and total internal reflection have also not been asked in quite some time, especially total internal reflection. And defects in vision, so long-sightedness, short-sightedness, this could be asked. Potential divider, using so analyzing that using the example that we just saw, ideas on power, Ohm's law, maybe for a filament lamp, and something I feel could possibly come in, so it's good to go with this prepared, is the idea of a diode. It was there in one of the IGCSE papers that we did most recently. So I feel that it could come in onto the O-level paper. Question number 9, I feel it could be one of these, most probably this one or this one, as an application of electromagnets. So how a moving coil loudspeaker, what's the idea of the EMF with it, how it produces sound, compressions, and rarefactions. There was a very similar question to this in a past paper that was in my worksheet on sound. DC motor explanation and the factors which affect the rate of rotation. This can also come in, because AC motors, AC generators have been coming in for quite some time. So I feel like this is the session in which DC motor reappears. Transformer equation, efficiency, and the ideas of high voltage transmission. Question number 10 is related to nuclear physics, so randomness, spontaneity, applications and analysis. Some suggest parts where you have to talk about how such a half-life would affect how much decay takes place, and the half-life calculation like the one we did, that could come in. And lastly, for question number 11, solar system has not been asked for quite some time, which is, for example, the different objects, the different celestial bodies in the solar system, how day and night are formed, what is the temperature variation, how does radiation from the sun affect what planets are hotter, what ones are not. Light year is definitely going to be on there, and redshift and the Big Bang theory. And for IGCSE, the accretion model. And now my throat is sore from speaking so fast, so much. So now it's your turn to ask if you guys have anything you want to clear up. All right. So by the way, this guest paper is not meant to scare you. It's not to say that all of this will be assessed. These are just some possible topics. The examiner also always keeps in mind that, for example, if he gives one hard question, maybe if electricity is harder, this means that the other questions will not be as hard, right? Maybe at max, you will have 2 or 3 parts which will require you to do some serious thinking. But do be wise in allocating your time. Don't just sit down and start like fighting with the question. Just go on, and if you have time, come back and do it then. All right, I see we have questions. My Insta is the physics junction. The physics junction. Okay. Everyone. How do I do everyone? Okay. So you can ask me on Insta as well, Saad, if you feel like you run into some problems or something. All right. So guys, that's it from my side. Best of luck. Be confident. That's the only advice I could give to you. Don't let any question take you down at this moment. Also, refrain from looking at the hardest questions that, for example, friends are sending out on WhatsApp groups, because that will mess with your confidence, right? Once you have all of your prep done by evening, if you feel like you are done with all of it, if you really, really want to still keep on studying, I suggest just go through some of the latest papers and their examiner reports just to know what mistakes not to do. Please do not, right when you're about to sleep, pull up a compilation of the most difficult past paper questions ever and start doing that. It will mess with your head. I guarantee this, right? So don't do this, please. Right now, don't look at any more harder papers. Look at a yearly paper, because that yearly paper will have a spread of easier questions and difficult questions. That's how your paper is going to be. We'll have some easy questions, some and really few, two or three difficult parts, right? So that's what you're supposed to do now. Don't look at difficult questions anymore. You've worked really hard, all of you guys, this entire year. Just chill out and go into paper fresh with a good night's sleep. All right. Thanks, guys, for those who joined. If you guys have any questions, please ask me out on Insta. Not ask me out. Ask me on Insta. Sorry. Slip. Uh, yes, Mahmood, I remember you. मैंने नाम पढ़ा तो I remembered this. All right. Thanks, guys, and best of luck. Allah Hafiz.